Again, Assalamu alaikum, and thanks to everyone. Thanks, Rabi, again to you for asking me to talk today. So during the next, we sorted it out in 45 minutes or so. I'll be talking on the recommendations given by AAPM and IAEA on for small field dosimetry. Okay. So in 2017, the International Atomic Energy Agency, or IAEA, and the AAPM jointly published a code of practice, also known as TRS 483. There's an executive summary of this code of practice was also published in Medical Physics in 2018, and here is the reference for that. So this slide here, it gives a list of the authors of the code of practice shown in red. And there are many other folks who also contributed to it. Their names are also here, and in the picture are shown at different times when we all met in Vienna, really working on this code of practice. So I'll give you a very brief overview of TRS 483 with really a lot of focus on the physics of the small field dosimetry. So what problems does TRS 483 code of practice solve? There are two main characteristics that led to dosimetric issues in small fields. These are reference dosimetry in non-standard fields and measurements of field output factor. So TRS 483 provided a formalism for both reference and relative dosimetry based on the work of Alfonso et al., and this is shown here, that was published in 2008, and a code of practice for dosimetry in reference fields that are not, say, 10 by 10, field size, SSD or SAD, not equals 100 centimeter. Machines such as gamma knives, cyber knives, that cannot set these conditions, we know that, right? And these fields are called machine-specific reference fields in the code of practice. The COP also provided a formalism and data for flattening filter-free beams and provided a method for beam quality specification for non-standard fields. The COP also provided a formalism and data for the determination of field output factors. This is perhaps the most significant contribution of the COP. So there are 6 chapters and 2 appendices. Chapter 1 is introduction, 2 is the physics of small field dosimetry. I'll spend a good bit of time in that for that chapter. Then concepts and formalism, detector and equipment, and chapter 5 and chapter 6 that deal with the code of practice for MSR field and relative dosimetry. There are 2 appendices, and the appendix 1 focuses on the determination of beam quality correction factors for reference dosimetry and their relative uncertainty estimates, and appendix 2 for the determination of field output correction factors and their uncertainty estimates. I recommend very strongly that, we usually have a tendency not to read the appendices, but this is where a lot of the meat is. So everybody really should read these appendices. So I'll talk about chapters 2, 3, 4, 5, and 6 very briefly. Let's start with the physics of small field dosimetry. So when is a field small? So there are 3 general conditions to consider if a photon beam can be classified as small. These are that there's a loss of lateral charge particle equilibrium in the region of interest. There's a partial occlusion of the primary photon source by the beam collimation system. This is a machine-specific issue. And then there's a mismatch between the detector size and the field size. And the perturbation correction factors for small fields are much larger than in a conventional broad radiotherapy beam. So let me talk about each of these conditions now. So loss of lateral charge particle equilibrium, or LCPE, that occurs in photon beams when the beam half-width or radius is smaller than the maximum lateral range of the secondary electrons. Lack of LCPE obviously is very problematic for dosimetry because the balance of charged particles scattered laterally in and outside of the beam fails. And this is shown schematically here. On the left, you see a broad photon field, and in the central region of interest, the number of particles entering and exiting the region of interest, they balance out because you're radiating a large field. Whereas if you have a narrow field, And since we are not radiating a large volume, the number of particles entering and exiting in the region of interest laterally, they do not balance out, and that's where the problem occurs. So the ratio of absorbed dose to collision kerma, or D/K call, can be used as a measure of the degree of CPE, or charge particle equilibrium, or transient charge particle equilibrium. What I've done here is plotted a ratio of dose over collision kerma as a function of the beam radius, or as a function of different beam energies. The minimum beam radius for which dose equals to collision kerma defines what is known as RLCPE. As you can see, as the beam energy increases from cobalt 60 to 24, for 24 MV, the RLCP is at about 2.5 centimeter, and cobalt 60 about 5 millimeter. So when one expresses this RLCP, one can do that as a function of the beam quality Q, and Q is TPR 2010, or percentage depth dose. That can be given by this equation where Q is either TPR 2010 or percentage depth dose, and A and B are the coefficients obtained from this fit from this Monte Carlo data. So what are some of the small field conditions? So small field conditions exist when the distance from the detector outer boundary to the field edge is less than a lateral charge particle equilibrium, or RLCPE. So here you see a field that is shown by the blue, and RLCPE is shown by this orange. In this case, this blue field will be a small field. If the detector size is D, then to achieve CPE, the full width half max must be larger than 2 times RLCPE plus D. This is an important condition for the fulfillment of TCPE. Okay. The second condition is partial source occlusion. On the left, you see a broad beam condition, and on the right, a narrow beam condition. For the broad beam, the field size is large. You can see the collimators open widely, and from the measurement point, you can see the entire radiation source. And there is no occlusion of the primary radiation source. And the field size set by this collimator matches the full width half max that we measure, say, at 10 cm depth. And the yellow color it shows the penumbra. On the right-hand side, now you bring the jaws together, and you have now a situation where the field size is small. From the measurement point, you cannot see the entire radiation source. So it causes an occlusion of the primary radiation source. And there is an overlap of the penumbra here, as you can see shown by the yellow color. And there's a relative increase of this penumbra. Both of these effects are related to this effective radiation source that you cannot see because of the occlusion. So there are consequences of this. An important consequence of this overlapping penumbra is that, contrary to broad beam geometry, where the field size, the full width half max that we measure at 10 cm depth matches what is said by the collimator setting. But on the other hand, in small field, the field size determined by the full width half max of a dose profile that we measure, say, at 10 cm depth and normalize to the central axis, this full width half max does not coincide with the jaw setting. Here, these blue arrows show what the collimator setting is, and here you see the full width half max is given by the red arrows. So there is an apparent widening of the field size. The full width half max is larger. And the other important thing is you see on the central axis, because there is a reduction in the beam output. It's because of this reason in the code of practice, the recommendation is that for small fields, the field sizes should not be identified by the collimator setting, but by the full width half max. So what are the issues of this decreasing field size? There are 2 important aspects that needs to be considered for the dosimetry of small photon fields. One is the hardening of the energy spectrum and its influence on the water to air stopping power ratios. So as the field size is decreased, the head scatter is reduced, and the phantom scatter is also reduced because we are irradiating a small phantom volume. What that does is this results in the filtration of the low energy photons and therefore the low energy electrons, and that increases the mean energy of the respective spectra. What you see here is a 6 MV photon spectra in a small volume of water for different field sizes ranging from 10 by 10 square centimeter to 0.5 by 0.5. As you can see, as the field size is decreased, this is for a 10 by 10, and this is for a 0.5 by 0.5, there's a significant filtration of the low energy component. And the mean energy increases from 1.3 MeV for a 10 by 10 to 2 MeV for this 0.5 by 0.5. So what impact does it have on stopping power ratio, this spectral hardening? Here I show you a plot of the water to air stopping power ratio on the vertical axis, very extended scale, versus depth for different field sizes. The good thing here that we see is that the variation in water to air stopping power ratio is actually pretty small, anywhere in it's less than 0.5%. So, and we knew about this for decades. There are many studies that have really established that. The recent ones is by Elkun and Hanso, and then Sanchez Doblado. So a conclusion from here is spectral hardening does not really to large changes in the water to air stopping power ratio. And so small fields then do not need a separate beam quality specifier. We only need a beam quality specifier in the MSR reference field. Then there are issues in small field that are related to chamber size. So one of the problems of ion chamber dosimetry in small field is a very important one is volume averaging effect. We all know that when you take measurements with an ion chamber, we get a reading. And this reading really is an average over the entire volume of the chamber. And this is proportional to the dose in the radiation sensitive volume due to the particles that cross this chamber. Now, if the field size is now made smaller than the detector dimensions, and particles cross only a small fraction of the sensitive volume, or the fluence over the detector volume is not uniform now, then the detector signal that we get average over its volume will clearly be incorrect. And so it really depends, this chamber reading depends on the chamber and field size ratio, and the volume averaging correction must account for that. Here I show you on the left an exciting S16 ion chamber, which has an inner diameter of 2.4 millimeter and outer diameter 3.4 millimeter, and the volume is 0.007 cc. You see that this chamber is put in a plot for gamma knife beams. This is the 18 millimeter helmet, and that's the 14 millimeter helmet. As you can see, when this detector, X-ray in S16, is placed in an 18 millimeter collimator, this detector is sampling the flat portion of the beam. So it's not a small field then, for this chamber when you use an 18 millimeter collimator. On the other hand, if you use it in a 4 millimeter collimator field, you see that there is a significant volume averaging because we are not sampling the flat portion of the beam. On the right, you see here is a plot of a hypothetical beam profile shown in blue, generated using an ideal detector. And the red profile shows a profile measured with a 5 centimeter long detector. Okay, so what you see here is that the central axis output goes down, and the full width half max measured with the red is smaller than what you see for the ideal situation. When you do reference dosimetry in broad beams, we know that the formalism for reference dosimetry in broad beams using ionization chamber is based on Bragg-Gray principle. And this is the equation that we see in TRS 398. And so there are different correction factors shown here. They actually account for the fluence perturbation introduced by the presence of the ionization chamber it has an air-filled cavity, it has a wall, it has a central electrode. So these perturbation correction factors corrects for those because of the placement of this chamber in homogeneous medium. We know from TRS 398 that these perturbation factors are independent and their values are small. Here you see a plot of this perturbation correction, overall perturbation factor as a function of beam quality. Anywhere from a TPR of 0.65 to 0.7, or beam energy approximately 6 MV to 10 MV, the range of perturbation factors is well within about 2%, except probably a few outliers. Or in other words, broad beam geometry, perturbation values of the perturbation factors are small and they're independent. Is it the case for small field situation? That is not. What I show you here, an example in a small beam, photon beam, the perturbation factors, you can see here the plot of the off-axis variation of the perturbation factors for a PTW pinpoint chamber 31006 with a steel electrode, for a 6 MV beam, 8 millimeter by 8 millimeter and 10 cm depth. At the central axis, where the absorbed dose or the reference dose is determined, you see the displacement correction shown in red is about 5%. And the volume averaging correction is another 5% or so. So the total perturbation correction factor becomes about 10%, which is significantly different than that we saw in the previous slide for broad beam geometry. So one can then summarize that the main issues with the use of ionization chamber in small field is really the large value that we get for volume averaging correction factor. So other detector related issues. So the need for a volume averaging correction, we need to minimize this. And how do you do that? One can use a smaller chamber size, making sure, remember that the distance from the field edge to the outer boundary of the detector, if you keep it less than RLCPE, that distance should be actually larger than RLCPE, then it should then create a situation of the field size that corresponds to charge particle equilibrium. So that is one way to ensure that we minimize the volume averaging correction. In other words, this is the condition that needs to be fulfilled. Then there are solid state detectors. We use diodes, say, for example, in the clinic all the time. And there are many advantages of these. These are the detectors that have a mass density that is much higher than that of an air-filled ionization chamber. And with that allows for the volume of this detector to be small because mass density is much higher. It allows for a much larger signal to noise ratio, high spatial resolution, but then minimizes the partial volume effects. So they're very appropriate for small field dosimetry. But there are again some issues that arise in relation with their intrinsic material and design. And because of those, for the smallest field sizes, that sometimes they require considerable correction factors. So chapter 3 deals with the formalism for the reference dosimetry. Similar to TRS 398, 3 approaches were considered for reference dosimetry in a MSR field, machine-specific reference field. Option 1, suppose the standard lab can give you an absorbed dose to water calibration coefficient. There are NDQ MSR. There's a lot of notation here. Those of you who are seeing it for the first time, it seems very confusing, but believe me, you get used to this. And we have to use this notation to really specify very clearly. So if standard labs can give you an NDWQ for your beam quality QMSR, then the absorbed dose to water at the reference depth in water under reference condition is simply given by this equation. Dose is M times NDW. M is the charge rating under reference conditions for the FMSR field and beam quality QMSR, corrected for the influence quantities. And D is the absorbed dose. And suppose that the standard labs, there's an option 2, provides you with an NDW for your chamber in a beam of quality Q0, where Q0 is cobalt 60. This is what you are used to in TRS 398. Then the absorbed dose to water at the reference depth 0F in water in a clinical beam of quality QMSR, and the field size FMSR is given by this equation. This QMSR Q0 FMSR FREF, it really corrects for the differences in the response of the ionization chamber between the response of the chamber at a cobalt 60 beam for reference beam field size 10 by 10, and the response of the chamber in your clinical beam of quality QMSR and field size FMSR. This option, similar to TRS 398, this option is intended to be used only when directly measured values or generic values of this KQ is available for different chambers. And these generic values should be provided by the standard labs. Now suppose that the standard labs provide you with an NDW, as in option 2, like here, but you don't have any beam quality correction factors for the machine that you are using. Really, so in that case, this third equation is the equation that will be used for the determination of the absorbed dose. So this equation gets a little bit of hairy. So what happens is, what you do is in option 3, then it requires you to determine a beam quality Q that is called a hypothetical beam and a conventional reference field FREF in the same machine that you're using for your clinical machine, where you have the MSR field and you have a beam quality QMSR. But you think of a hypothetical beam in the same machine of a beam quality Q and field size FREF of 10 by 10. This KQ-Q0 FREF then corrects for the differences in the response of the chamber in this hypothetical beam of quality Q and the Q0 that is cobalt 60. And then you need a second beam quality correction factor that corrects for the differences in the response of the chamber in this hypothetical beam of quality Q and the clinical beam that you're interested in, QMSR. So, and the code of practice gives a method, and I'll talk about that a little later, on how to determine this hypothetical beam quality Q. When it comes to flattening filter free beam, the formalism is essentially identical. However, the complication arises because this value of KQ-Q0FREF that we have say in TRS 398, that is for beams with that are flat. So, but the code of practice provided tabulated data, for and broken this KQ-Q0 into different components so that it takes into account for the flattening filter free beams. So what are some of these contributions? The main issues that leads to this KQ-Q0 data, the differences between beams with flattening filter and beams without flattening filter, are that there's a difference in the water to air stopping power ratio as a function of beam quality between WFFF and FFF beams. And there are differences in the ionization chamber perturbation correction factors as a function of beam quality. And of course, what I mentioned, an important difference is also the volume averaging correction due to this non-uniform lateral beam profile of this, the flattening filter free beam. Here you see the data for water to air stopping power ratio for a clinical FFF beam. These are the data points, and that is for the WFFF beam. So you see that there's a difference in water to air stopping power ratio, and the solid line is a fit that was used to calculate the difference between these two. Okay, and this difference is applied in TRS 483 to account for the differences between WFFF beam and the flattening filter free beams. So as I mentioned, the formalism is identical for FFF beam, but to make things easier, and as I mentioned, that the complication comes from this KQQ0 for the FFF beam. So the code of practice broke this down into two components, is shown here. One of them corresponds to a hypothetical beam, a flattening filter-free beam, and a hypothetical beam with flattening filter, both in the same machine, and where you are considering your MSR field. And this KQ corrects for the differences between these two beam qualities. And the second one, this one corrects for the difference in the response of the chamber in the beam quality, the WFF beam and the beam quality Q0. Yes, it gets a little hairy, but believe me, once you read a bit carefully, eventually, one is able to understand the details. And this beam quality Q, this difference arises because one is a flattening filter-free beam and one is a WFF beam, so the spectrum is different. And these differences in spectrum correspond to differences in the water-to-air stopping power ratio, perturbation factor, and volume averaging. Chapter 4 deals with detector and equipment. And it gives a detailed descriptions of what kind of equipment to use for small field dosimetry and what kind of detectors mostly. There's a lot. Frequently, everybody will be asking, what kind of detector do I use? So I suggest that read chapter 6 very carefully, and that will give you a full description as to what kind of detector one should be using for small field dosimetry. The MSR field is divided into two for FMSR greater than or equals to 6 cm by 6 cm and less than 6 cm by 6 cm. And the chapter again recommends what kind of detectors to use for field sizes greater than 6 cm by 6 cm and smaller than that. For small field, they recommend the code of practice states unequivocally that there is not an ideal detector that is good for all kinds of parameters that we want to measure for small field situation. So the recommendation is always use 2 or 3 different detector types and do the measurements for the parameters, the field output factor that you want to measure, and make sure that there is redundancy in the data, and that will give confidence in the data that you're measuring. Here's an example of the taken from the tables of the detectors that are recommended, say, for example, for field sizes greater than 6 by 6. Remember, for MSR field, this condition needs to be fulfilled. So there's a long list of detectors. And similarly, and that's table 4 in the COP. Similarly, there's a long list of detectors when the field size is less than 6 cm by 6 cm. For these field sizes, the chamber volume ranges from 0.3 cc to 1 cc. And for this field sizes smaller than 6 by 6, the chamber volume is less than 0.3 cc, and the largest cavity dimension is restricted to less than 7 millimeter. And this ensures that for 10 MV beam, a 4 cm equivalent square MSR field, I'll talk about that shortly, will fulfill the condition of RLCPE. That's what is shown here. And for a 6 MV beam, it will fulfill the condition of RLCPE for a 3 cm equivalent square MSR field. I'll talk about what I mean by equivalent square MSR field shortly. For small field, there's again another table here, and you see a lot of diodes that are shown here, and these are the characteristics. So the ion chambers with volume from 0.3 to 0.6 cc, they're not suitable for relative dosimetry in small fields. Their volume is too large, as I mentioned, and they underestimate the dose on central axis in a small field. Ion chambers with volume between 0.01 and 0.3 cc, these are micro chambers and pinpoint chambers. They're suitable for measurements of different parameters for small field, for field sizes down to 2 by 2, 2 cm by 2 cm. And then microionization chamber with volumes between 0.002 and 0.01 cc, these are micro chambers. They have a very small measuring volume, obviously, as you can see, and so they have a very small volume averaging effect. But since their volume is very small, there's a problem with their sensitivity. Okay, so there's a balance between the two. And again, chapter 4 gives you detail about that. Chapter 5 talks about it's a clinical implementation, how you really, in the clinic, when you really do the reference dosimetry in the MSR field, this is a chapter that gives you step-by-step guidance. Remember, I said that there are 3 approaches that were recommended. Approach 1 is, even though that's the preferred approach, there are not many standard labs that can really provide you an NDW QMSR, for the clinical beam of quality QMSR. So until that's available, then chapter 2 and 3, options 2 and 3 are the 2 options that one uses. I need to mention that there are actually a few primary standard labs who are providing NDWQ MSR, but that's still at a very early phase. So in order to do reference dosimetry, you need to know the values of the beam quality correction factors for different ionization chamber, depending on which options you use. And you need to know the beam quality for both reference dosimetry, for the measurements of, you need the reference conditions for measurements of reference dosimetry, and you need to know the beam quality so that you can get the values of KQ in these MSR fields. The code of practice gives you a lot of tables for the reference conditions. Here is an example of the reference condition for the determination of absorbed dose to water in high energy photon beams. Water is the phantom material. Chamber recommended cylindrical reference depth is 10 grams per square centimeter, and gives you some other information. SST and STD should be 100 centimeter or as close as possible. Field size, if you have a 10 by 10, that's the ideal. But if you don't, then the largest field size is the MSR field size. For example, if you have a cyber knife, and the next slide actually shows what are some of the MSR fields for different radiotherapy machines. For a cyber knife, your MSR field is 6 cm diameter fixed collimator. For a tomotherapy, 5 cm by 10 cm. Gamma knife, it can be 16 millimeter or 18 millimeter, and so on. So let's talk about beam quality. For conventional reference field, like when you use TRS-398, you have a 10 by 10 field, you have a 100 SSD or SAD. TRS-398 tells you how to measure beam quality, say TPR 2010. But how do you determine beam quality for non-standard MSR fields, like CyberKnife? Your field size is 6 cm circular diameter, right? You cannot set a 100 SAD. So what do you do in those cases? So TRS-483 gives you a method for beam quality. And what you do is, this is the TPR 2010. This is the hypothetical beam quality. You measure a TPR 2010 for the MSR field, and then use this equation. S is an important parameter. This is equivalent square MSR field. It's important terminology. Equivalent square MSR field. What is an equivalent square MSR field? So when you have a non-square field size, like say 6 cm circular field, right? The equivalent square MSR field corresponds to that field for which the phantom scatter for the non-square field and the square field is the same. And so the code of practice gives you a prescription on how to determine this value of S for the non-standard field that you're dealing with. If you're dealing with the CyberKnife 6 cm circle, the code of practice tells you what S is, the equivalent square for a 6 cm circle. It happens to be 5 centimeters. So what you do to get the beam quality, you measure this TPR 2010 for your MSR field, you get the value of S, and the values of these coefficients D are given, and you get the beam quality TPR 2010. This is your hypothetical beam that I've been talking about earlier on. And there's similar different formula for percentage step dose 10x. For the measurement of the beam quality, it's again the same setup that for TPR 2010, say, as we do for TRS-398. The only difference is you would do these measurements in an MSR field now, not necessarily a 10 by 10. And you just need to determine the value of S, the equivalent square MSR field. Okay, so you take your measurements at 10 cm and 20 cm depth, and you get the value of your TPR 2010. So to summarize, for the reference dosimetry measurements in an MSR field, what you have to do that you get your NDW Q0 for your ionization chamber, get your equivalent square MSR field by looking at the code of practice, measure your TPR 2010 in the MSR field, if you are using that as your beam quality specifier, and then you calculate this hypothetical beam quality TPR 2010. Then you look up the values of the beam quality correction factors given as a function, sorry, I went too far back, sorry, given as a function of this beam quality. I would like to emphasize that people have made a lot of mistakes by not reading the captions of the tables. It is critical that when you're looking up these values of KQ, there are many tables. Please read the table captions very critically. Otherwise, there is the significant potential that you'll be making mistakes. Chapter 6 deals with relative dosimetry. It's the measurement of field output factors in small field. This is perhaps the most significant contribution of the code of practice. So we know that the field output factor for a clinical field, F-Sclin, shown here by this notation, is defined as the ratio of absorbed doses in the clinical field to that in the reference field. It can be an MSR field or it's a reference field, and this is omega notation. So it's a ratio of absorbed doses. This can be expressed as a ratio of the charge reading, Q clinical, in the clinical field and the reference field, multiplied by the correction factor. What we do in the clinic now, when you measure, say, for example, output factor for, say, 3 by 3 field size, we take a ratio of charge reading between 3 by 3 and 10 by 10. We just do this. And this is good in broad beam geometry, as long as this correction factor is small or unity. But as I have shown you so far, that the correction factor, this output correction factor can be very large. The volume averaging correction, the perturbation factors, they all become very large in small fields. And there has been a lot of accidents in the community because we measured the output factor for small field by taking ratio of readings and using large volume ionization chamber, for example, a farmer type chamber. And these resulted significant deviation, underestimate of the output factor, and there are a lot of accidents that have been reported in the literature. So it's critically important that we pay close attention to this output correction factor. Now, and they are given in different tables. And this output correction factor is given in the code of practice against a parameter called Sclin. And what is Sclin? Let me see. So Sclin is known as equivalent square small field. Notice I said equivalent square small field as opposed to equivalent square MSR field, which is what I talked about when I talked about the beam quality. So there's a critical difference between the two. So output correction factors are plotted as a function of Sclin because the published data show that for small field, when you plot them as a function of equivalent square small field, the perturbation factors are the same in the non-square field and the square field. And this Sclin is given by this equation, square root of A times B, where A and B are the full width half max that you measure, say, in the in-plane and the cross-plane direction. So remember I said early on, you need to measure full width half max. So, and measurement of full width half max in small field is really not an easy thing. You have to be very careful as to how you measure that. The chapter 6 really gives a detailed description on how to set up the water tank, how do you align your water tank, how do you set up your, how do you orient your detector. So please read those very carefully, measure that Sclin very critically, and calculate, get the full width half max, and get your value of Sclin. So for measurements of field output factor, so what we do is you obviously choose a recommended detector, recommended in the code of practice. You set up your water phantom. As I mentioned, make sure that you are orienting the detector correctly, positioning it correctly, and you measure the beam profile very critically. And then once you've measured that, then you calculate a Sclin from the square root of the full width half max, if you're using a rectangular field. And for a circular field, it's also an equation as I've shown you in the previous slide. Then the output correction factors, they have been calculated from the data that were available to us during the period, when we're developing this code of practice. This KQ is given as a function of Sclin. So you have now the conditions. You measure the charge reading between clinical field and the reference field, and you multiply by the correction factors. Here is an example of what the output correction factors look like. Here, the vertical axis is the output correction factors, the values of this, the KQ clean, QMSR, F clean, FMSR. Those are the output correction factors, right? They are plotted here, this is the vertical axis, and horizontal axis is the S-clean. So there are lots of data. This is for a particular IBA SFT unshielded diode. So the solid line here takes an weighted mean of the data that were available in the literature at the time of writing the code of practice. And this vertical, the solid lines here, they represent the combined expanded uncertainty and for each of these data with a 95% confidence level. And at each plot, you'll see a horizontal line here. And it's important. That corresponds to an uncertainty, the value of this, where the uncertainty is 2 in plus or minus 5%. That sets the limit. So if the data that we found were the values in the literature for the different output correction factors are more than plus or minus 5%, those were not included in the code of practice. And you'll see when you look at the table, there are a lot of dashed lines, there are no data there available. So there are lots of plots given in the code of practice. Here is just an example. Here is another example for the PTW diode and sun nuclear diode. And the data are also given in a tabulated form. Then to summarize then, this is really the first code of practice for the dosimetry of small photon fields. And it really took us over 10 years to develop this code of practice. And this code of practice gives you recommendation for reference dosimetry for radiotherapy machines that cannot establish a conventional 10 by 10 reference field. And it also gives you the output correction factor data for relative dosimetry. And as I said, perhaps this is the most significant contribution because there's a lot of data in the literature where you saw these output correction factors were significantly different from chamber to chamber, which led to many accidents in the community. With that, I thank you again for